Welcome back. Last episode, the spectral theorem gave us a perfect factorization, but only for square symmetric matrices. Today we remove every restriction. The singular value decomposition applies to any matrix whatsoever: tall, wide, square, singular, full rank, or rank 1. It says that any matrix A can be written as U times sigma times B transpose, where U and V are orthogonal, pure rotations, and sigma is diagonal with non-negative entries called the singular values. Geometrically, it is the cleanest statement imaginable. Every matrix is a rotation, then a stretch along perpendicular axes, then another rotation. The unforgettable picture is that a matrix takes the unit sphere and turns it into an ellipsoid. We will build the SVD from the spectral theorem applied to A transpose A, read off where the singular values come from, and then reach the Eckart Young theorem. The reason the SVD is the single most useful factorization in data science. Let's begin. Here is the precise statement. Every real matrix A with m rows and n columns can be written as U times sigma times V transpose. U is a square orthogonal matrix of size m by m, and its columns are called the left singular vectors. V is a square orthogonal matrix of size n by n, and its columns are called the right singular vectors. In between sits sigma, the same shape as A, which is diagonal in the sense that its only non-zero entries sit in the top left diagonal positions. Those entries are the singular values, written sigma 1, sigma 2, and so on, and we always list them in decreasing order, all non-negative. A beautiful bonus, the number of non-zero singular values is exactly the rank of A. Compare this to eigenvalue diagonalization, which demands a square matrix and can still fail. The SVD asks for nothing: no symmetry, no squareness, no diagonalizability. For every matrix that exists, this factorization exists. That universality is what makes it so powerful. Before we read off the pieces, let's understand why A transpose A is the magic ingredient. Take any matrix A whatsoever, even a wildly rectangular one with no eigenvalues of its own. Form A transpose times A. Three things are guaranteed. First, the product is square, of size n by n, where n is the number of columns of A, so it has eigenvalues even when A does not. Second, it is symmetric, because transposing A transpose A gives back A transpose A. Third, it is positive semi-definite. The quadratic form x transpose times A transpose A times x is just the squared length of A times x, which can never be negative. Those last two facts are exactly the hypotheses of the spectral theorem from last episode. So A transpose A has real, non-negative eigenvalues and perpendicular eigenvectors. Because the eigenvalues cannot be negative, their square roots are real, and those square roots are the singular values. This is the bridge across the gap. A rectangular matrix has no eigenvalues, but A transpose A does, and they quietly deliver everything the SVD needs. The geometry is the heart of the SVD. Read the factorization from right to left acting on a vector. First, B transpose rotates space so the right singular vectors line up with the coordinate axes. Then sigma stretches. Each axis is multiplied by its singular value, so a sphere is squashed and stretched into an ellipsoid. Then U rotates that ellipsoid into its final orientation. So the single most important picture in this episode is this. Take the unit sphere, all vectors of length 1, and apply any matrix. The image is always an ellipsoid. The directions of its semi-axes are the left singular vectors, the U's. The lengths of its semi-axes are the singular values, the sigmas. And the right singular vectors, the V's, are the perpendicular directions in the original sphere that get mapped to those axes. In one sentence, every linear map, no matter how complicated it looks, is just rotate, stretch along perpendicular axes, rotate. There is nothing else a matrix can do. Where do the singular values and vectors actually come from? From the spectral theorem of last episode. Take any matrix A and form A transpose times A. This product is always symmetric, and it is always positive semi-definite, so by the spectral theorem it has an orthonormal set of eigenvectors and real, non-negative eigenvalues. Write A transpose A equals V lambda V transpose. Now read off the SVD. The singular values are the square roots of those eigenvalues. Sigma I equals the square root of lambda I. The right singular vectors, the columns of V, are exactly the eigenvectors of A transpose A, and the left singular vectors come from pushing each right singular vector through A and normalizing Ui equals A times Vi divided by sigma I. You can check that these U vectors come out orthonormal automatically, and that the relation A times Vi equals sigma I times Ui, gathered over all I, is precisely the equation A equals U sigma V transpose. So the entire SVD is the spectral theorem of A transpose A in disguise. Symmetry built the foundation, the SVD stands on it. Here is the SVD on one canvas, in 2 dimensions. On the left, the unit circle, and through its center, two perpendicular arrows, v1 and v2, the right singular vectors. These are the special perpendicular directions that the matrix treats cleanly. On the right, after applying the matrix A, the circle has become a tilted ellipse. The two perpendicular arrows have become the two semi-axes of that ellipse. The arrow v1 maps to sigma 1 times u11. Its direction is the left singular vector u1, and its length is the singular value sigma 1, the long semi-axis. The arrow v2 maps to sigma 2 times u2, the short semi-axis. Perpendicular went in and perpendicular came out, only stretched and rotated. That preservation of right angles both before and after is the special gift of the singular vectors. Any other pair of perpendicular directions would generally come out skewed. This picture is the SVD. The v's are the input axes, the sigma u's are the output axes, and the matrix simply maps one perpendicular frame to another, scaling as it goes. It is worth pausing to compare singular values with the eigenvalues we studied earlier, because students often confuse them. Eigenvalues exist only for square matrices. They can be negative or even complex, and their eigenvectors need not be perpendicular. Singular values, by contrast, exist for absolutely any matrix. They are always real and non-negative, and their singular vectors are always perfectly orthonormal. So the SVD is the more universal and better behaved notion of the size of a matrix. When do the two agree? Exactly when the matrix is symmetric. For a symmetric matrix, each singular value is the absolute value of the corresponding eigenvalue. The SVD simply strips off the sign and tucks it into one of the rotation matrices. So the spectral theorem is the special case of the SVD where the input and output rotations are the same. Think of the singular values as the honest, unsigned stretch factors of a matrix, a clean list of non-negative numbers that exists and means the same thing for every matrix there is. A matrix of rank R has only R non-zero singular values. The rest are zero and contribute nothing. So we can throw away the dead columns and keep the reduced SVD, using only the first R singular values and their vectors. This gives the most illuminating form of all. A is a sum of R rank 1 pieces. Each piece is a singular value times the outer product of a left singular vector with a right singular vector, a single rank, one layer. And because we ordered the singular values from largest to smallest, these layers come sorted by importance, the most significant first. This form also lays bare the four fundamental subspaces from earlier in the course. The column space of A is spanned by the first R left singular vectors. The row space is spanned by the first R right singular vectors. And the null space is spanned by the leftover right singular vectors, the ones whose singular value is 0. Everything we learned about subspaces is sitting inside this one decomposition, neatly sorted and orthonormal. Now the payoff that makes the SVD the most useful tool in applied linear algebra. Take the rank 1 sum and keep only the first k terms, the k largest singular values, and discard the rest. Call the result A sub k. The Eckart Young theorem makes a remarkable promise. A sub k is the single best rank k approximation of A that exists. Among all matrices of rank k or less, none is closer to A. And the error you incur is governed by the very first singular value you threw away, sigma k plus 1. So if the singular values decay quickly, which real data almost always does, a handful of terms captures nearly all of the matrix. Think about the savings. A full m by n matrix needs m times n numbers. The rank k approximation needs only about k times the quantity m plus n. When k is small, that is a dramatic compression. This one theorem is why the SVD compresses images, filters noise out of measurements, and shrinks gigantic data matrices down to their essential structure. You keep the loud signals and drop the quiet ones, and mathematics guarantees you have lost as little as possible. Here is the same idea one dimension up, in three-dimensional space, where it becomes truly vivid. On the left, the unit sphere, all vectors of length, 1, with three mutually perpendicular arrows along its axes, the right singular vectors. Apply the matrix A, and the sphere deforms into the ellipsoid on the right. The three perpendicular arrows become the three semi-axes of that ellipsoid, each pointing along a left singular vector and each stretched to the length of its singular value. The longest semi-axis is sigma 1, the next sigma 2, the shortest sigma 3. Perpendicular went in and perpendicular came out, scaled along the way. This is the complete geometric content of the singular value decomposition, no matter how tangled a matrix looks. It takes the round unit sphere and produces an ellipsoid, and the singular values are simply the lengths of that ellipsoid's semi-axes. If a singular value is 0, that axis collapses flat and the ellipsoid loses a dimension, which is exactly how the SVD reveals the rank. Let's compute some singular values. Start with the easy case, a diagonal matrix with 2 and 3 on the diagonal. A diagonal matrix with positive entries is already a pure stretch, so its singular values are just those entries, listed in decreasing order, 3 and 2. The singular vectors are the coordinate axes, possibly reordered so the larger stretch comes first. Now, a genuinely non-symmetric matrix, 1's on the diagonal, a 1 in the top right, a 0 in the bottom left, a shear. Form A transpose A, you get a symmetric matrix with 1 in the top row and 1, 2 in the bottom row. Its eigenvalues are 3 plus or minus the square root of 5 all over 2. The singular values are the square roots of those, about 1.618 and about 0.618. Here is a lovely sanity check. The product of the singular values is 1, and the absolute value of the determinant of A is also 1. That is no accident. The product of all singular values always equals the absolute value of the determinant, because the determinant is how much a matrix scales volume, and the singular values are exactly the per-axis stretch factors. Here is the real strength, a non-square matrix, handled by exactly the same recipe. Take a 3x2 matrix, 3 rows, 2 columns. The trick is to form A transpose A, which is the small product, only 2x2. Here it comes out diagonal with 2 and 1 on the diagonal, so its eigenvalues are 2 and 1, and the singular values are their square roots, the square root of 2 and 1. The right singular vectors are the eigenvectors of that 2x2, which are just the standard axes, the vector 1, 0, and the vector 0, 1. To get the left singular vectors, push each right singular vector through A and divide by its singular value. The first gives 1 over root 2 times the vector 1, 0, 1, living up in 3-dimensional space. The second gives the vector 0, 1, 0. Notice the left singular vectors live in the 3-dimensional output space, and the right singular vectors live in the 2-dimensional input space. They are allowed to live in different spaces because the matrix is rectangular. 2 non-zero singular values means the rank is 2. The recipe never changed, only the shapes did. Let's make Eckart Young concrete with image compression. A grayscale image is just a grid of pixel brightness values, so a 1000 by 1000 image is a matrix with 1,000,000 entries. Now take its singular value decomposition and keep only the 50 largest singular values, discarding the rest. The compressed image is the rank 50 sum of those 50 layers. To store it, you only need the 50 singular values together with their left and right singular vectors, about 100,000 numbers instead of 1,000,000, roughly a 10-fold saving, and far more for higher resolutions. What do those layers mean visually? The large singular values capture the broad shapes and big regions of the image, the parts your eye notices first. The small singular values carry fine texture and sharp edges. By Eckart Young, the error from truncating is just the size of the first singular value you dropped, which for natural images is usually tiny, so the compressed picture looks almost identical. This very same idea, keep the strong patterns, drop the weak ones, drives denoising, recommender systems, and latent semantic analysis, which are exactly where the finale takes us next. The SVD keeps giving. 2 more gifts before the history. First, the pseudo-inverse. A rectangular or singular matrix has no true inverse, but the SVD lets us build the next best thing, keep V and U, and invert sigma as far as possible by replacing each non-zero singular value with its reciprocal and leaving the zeros alone. The result, written A+, is the pseudo-inverse, and multiplying B by it gives exactly the least square solution we worked so hard for back in episode 27. Here, it falls out in one line. Second, the condition number. Define it as the largest singular value divided by the smallest. This single number tells you how trustworthy the matrix is to compute with. If all the singular values are comfortably large, the matrix is well conditioned and solving systems with it is stable. But if the smallest singular value is close to 0, the matrix is nearly singular, the condition number blows up, and tiny errors in your data get amplified enormously in the answer. The singular values, in other words, measure how invertible and how reliable a matrix really is. A short history. The singular value decomposition was found astonishingly early. In 1873, the Italian mathematician Eugenio Beltrami discovered it for real square matrices while studying bilinear forms, and Camille Jordan found it independently just a year later. James Joseph Sylvester rediscovered it again in 1889, calling the singular values canonical multipliers. In the early 20th century, Léon Auton extended it to complex matrices, and then, in 1936, Carl Eckart and Gail Young extended it to rectangular matrices and proved the theorem that bears their names, that truncating the SVD gives the best low-rank approximation. But the SVD only became a practical everyday tool in 1965, when Jean Golub and William Kahan published a numerically stable algorithm to compute it. That algorithm turned a 19th century curiosity about bilinear forms into the computational backbone of modern data science, signal processing, and machine learning. Few ideas have traveled so far from where they started. Let's recap. The singular value decomposition writes any matrix A as U times sigma times V transpose, with U and V orthogonal and sigma diagonal with non-negative singular values in decreasing order. Geometrically, it is rotate, stretch, rotate, and it sends the unit sphere to an ellipsoid whose semi-axis lengths are the singular values. The pieces come from the spectral theorem applied to A transpose A. The singular values are the square roots of its eigenvalues, the right singular vectors are its eigenvectors, and the left singular vectors are their normalized images under A. The decomposition is a sum of rank 1 layers ordered by importance, and the count of non-zero singular values is the rank. The Eckart Young theorem says truncating to the top k layers gives the best possible rank A approximation, with error equal to the first singular value you dropped, which is why the SVD compresses, denoises, and reveals structure. Next episode is the series finale. We aim the SVD at real data, center it, and arrive at principal component analysis, and we close the whole course. Today we found the decomposition that worked for every matrix. The singular value decomposition says that any matrix A, of any shape, can be factored as A equals U times sigma times V transpose. Here, U and V are orthogonal matrices, pure rotations, possibly with a reflection, and sigma is a diagonal matrix whose entries, the singular values, are non-negative and listed in decreasing order. Geometrically, the meaning is unforgettable. Every matrix takes the unit sphere and maps it to an ellipsoid. V transpose rotates, sigma stretches each axis by a singular value, and U rotates again. The singular values are the lengths of the ellipsoid's semi-axes. Where do they come from? From the spectral theorem. The matrix A transpose A is symmetric and positive semi-definite, so it has real, non-negative eigenvalues. The singular values of A are the square roots of those eigenvalues. The right singular vectors, the columns of V, are the eigenvectors of A transpose A, and the left singular vectors, the columns of U, are the normalized images of those vectors under A. The biggest payoff is the Eckart Young theorem. If you keep only the largest few singular values and throw the rest away, you get the best possible low-rank approximation of the matrix. That single idea compresses images, filters noise, and powers recommendation engines. Next episode, the series finale, we point the SVD at real data and arrive at principal component analysis. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.